Hello, my name is Timothy Finnegan, and I will be presenting for Team Rocket for this OpenWERX challenge. Our team is made up of students from the University of Alabama in Huntsville AUVSI Pathfinder Student Chapter. Our objective for this project was to look at the DJI Phantoms 3 and 4 and discover the potential vulnerabilities in those products. Within the past few years, drones have become more accessible than ever, and as a result, more accessible to malicious entities. For this project, we intend to identify means of gaining control over aircraft being operated by those malicious entities. In order to better understand the problem, we broke down the vehicle into three categories: hardware, software, and operational. The hardware for the DJI Phantom 3 and 4 is nothing special. It is all hobby-grade hardware. It is not hardened in any way, and it has limited performance. The software running on the Phantom is also not hardened, uses basic encryption, relies on TCP/IP protocols for communication between the vehicle, the controller, and the mobile device app. It uses the Mavlink framework for issuing commands, which has known exploits, and uses OpenWRT, which is also exploitable. Operationally, users of these products that wish to do harm are going to potentially be inexperienced, which would lead to a hasty or improper configuration of the hardware. And given those two, they would also have a low level of confidence in their piloting ability. To defeat the software, we propose three different vectors. GPS is the first and probably easiest to work with. One option would be to spoof the GPS coordinates. Another would be to create local interference, triggering some sort of link loss with the satellites. Another vector would be optical avoidance. The software running on the newer Phantoms incorporates additional sensors which prevent any kind of collision with incoming objects. In order to trigger that part of the algorithm in the flight controller, a potential solution would be to confront it with a physical object. Another vector would be the data or control link. The local interference and link loss option is also available, but a more interesting approach would be to attempt a takeover of the vehicle. Since the vehicle uses TCP/IP protocols, it is vulnerable to standard network attacks. In addition to hacking the drone, the mobile app that connects with the Phantom is also vulnerable in several ways, namely a default password of 1234 1234. For hardware attacks, we looked at several options. The first was electromagnetic interference. We feel that if you were to induce a strong enough magnetic field near the equipment, the motors would desync and either stop spinning or spin uncontrollably. Another vector would be the optical sensors. The sensor itself on the camera could be disrupted with directed light, such as a laser pointer, or the camera could be blocked or disabled entirely, preventing the pilot's ability to fly beyond line of sight. Another vector would be to tamper with operational feedback. An inexperienced pilot will be relying upon feedback provided by the system to pilot it to its destination. By creating local interference such as noise or light, or introducing obstacles such as birds, you could prevent the operator from piloting the vehicle effectively. Social engineering also occurred to us as a potential attack vector. By preying upon the inexperience and lack of confidence in the pilot, you could potentially force the pilot to abort their mission and pilot it back to their home location. To reiterate, we've identified several attack vectors for both the operations of piloting an unmanned vehicle, the hardware, and the software for that unmanned vehicle. Thank you.